Today we're going to talk about a way to use Stokes' theorem in a really tricky way, in a really sneaky way. And by the end of the day, we're going to use this really sneaky way to apply Stokes' theorem to change the surface of a surface integral. And let's do an example to demonstrate what I mean here. We've got this vector field, f of x, y, z, and the vector field is given by x squared y, 2yz, z squared. Let S be the surface formed by taking the surface of the unit cube stretching from 0 to 1 in both the x, the y, and the z directions, and delete the bottom of that cube. Then orient the surface outward. By any means, calculate the surface integral of the curl of f. Alright, now let's just get our handle on things now. Here is the xyz axes, and we have this cube that stretches from 0 to 1 in every direction. So I'm just sketching it in. Now someone has gone and they have deleted the bottom of this cube, and so that leaves us with a boundary curve, which I will call C, which I'll draw in red here. Here's the boundary curve. So here, this cube has 5 walls. The bottom wall has been deleted, but it still has its front, back, left, right, and top walls. Now they say to me, we have oriented this cube in the outward direction. So let's see what it would take in terms of orientation of the boundary curve for us to have our head pointing in the direction of the normal vector and to have the surface on our left. And I think that if I point my thumb in the direction of the normal vector and my middle finger curls toward that gray vector, that forces my index finger to point in the direction indicated by the red arrows that I'm drawing. Here is the orientation of this curve C. So, according to Stokes' theorem, we could calculate this surface integral by transforming it into the line integral over C of the function f dr. And at first glance, it might seem like this will save us a lot of work, for 2 reasons. One, the line integral is not going to require us to have actually calculated the curl of f, which can take some time. But not only that, if I were going to calculate the original surface integral, notice that I would need to do this 5 times. 5 different surface integrals. 5 surface integrals which correspond to the 5 walls of this cube, each of which is going to have their own parameterization, because anytime we encounter a sharp corner or an edge or a cusp in mathematics, that corresponds to an abrupt change in behavior, and so we need a new parameterization to describe the new behavior. Alright, so the original surface integral seems absolutely miserable. But let's think about this line integral, shall we? Since the boundary of this cube is a square, to calculate the line integral on this 4-sided square, that's going to require 4 line integrals. So the idea is to use Stokes' theorem one more time. we redraw our boundary. Stokes' theorem says, hey, that line integral over C, which would be so complicated, can be replaced by a surface integral. But I'm not going to take the integral over the original cube surface. I'm going to take the surface integral over a different surface, which I might call S prime, a simpler surface that has the same boundary as the first one. And I'm going to take the surface, the flat one, that lives in the xy plane, this beautiful, simple, easy surface in the xy plane has the same C as its boundary. So by using Stokes twice, we were able to take a terrible surface integral and it turned it into a slightly less terrible line integral. And then by using Stokes' theorem a second time, we were able to turn that slightly less terrible line integral into a surface integral that's now not so bad. So we can calculate the surface integral over the new surface of curl S, and because this surface is smooth and flat and well behaved, we would only need one surface integral using S prime. Alright, so let's get a parameterization for S prime. And this one comes pretty cheap because the z coordinate is constant at 0, and this bottom of the cube lies entirely in the xy plane. And then x and y are once again free to act as our parameters. So x can be u and y can be v. And let's recall that x and y stretch between 0 and 1. And so the same thing will be true for our u and v. This is the set of all u's and v's. Now based on that parameterization, we have a ru, which is 1 for x and 0 for the rest. We have an RV, which is 0, 1, 0. So I and j. And the cross product of I and j is always equal to the vector k. Or 0, 0, 1. Now let's make sure that the orientation here, this normal vector, matches the orientation of our boundary curve. If we go around the boundary curve and our head is pointing straight up, then yes indeed the surface will be on our left side as we do that. So this is the correct orientation. Okay, so we have now found RU cross RV. Let's go ahead and find the curl of our vector field, which is x squared y, 2yz, and z squared. X squared y, 2yz, z squared. Calculating the curl. We have our partials, partial x, partial y, partial z. So partial y of z squared is nothing. Partial z of 2y squared subtracted 2y. And then for j we have 0, it looks like. And then for k we have 0 minus x squared. And in terms of our parameterization, this would be negative 2v, 0, negative u squared. And so if we dot product the curl with our normal vector, curl f, dot product ru cross rv, then the x component contributes nothing, the y component doesn't contribute anything, and we get from the z component negative u squared. And so it remains to calculate the double integral over the region D of negative u squared. Now D just had u and v going from 0 to 1. And so we get negative u cubed over 3 from 0 to 1, which is negative 1/3 integrated from 0 to 1, which is negative 1/3. And that number is the result of calculating the flux of curl F through this box with its bottom cut off. Same number that we would get by calculating the line integral of F over the boundary of the square, which in turn is the same as calculating the surface integral over this convenient square. Now, that is a wonderful trick, really quite something to say, I don't like this surface, and I don't like this boundary curve either, so let me use Stokes Theorem twice to switch from one surface integral to another surface integral that's going to be much nicer.